In our previous part, we have completed two portions or two parts for our given problems over here, and I have got the same problem over here, but the last part is been very lengthy over here. That is why I have separately considered this as a C point, and I have already eliminated the A and B portion over there. Why? Because I have already solved that. If you have missed our previous videos, previous solutions regarding our A and B, please do follow our previous videos. Now get back towards our present problem over here, which is determine the deflection of the galvanometer when the unknown resistance R is changed by 0.1% from its value at balance. The galvanometer has a sensitivity of 200 millimeter per microamps. Okay, so this is our sensitivity values, and that deflection part that will be come later over there. I have already given you how to solve the unbalanced condition for our Kelvin double bridge and how to get to that equation of our, say, I have utilized the Thevenin's theorem, and after I have applied the Thevenin's theorem, I have got the voltage as our E0. E0 is nothing but the EAB minus EAMD, and EAB is this one, P divided by P plus Q multiplied with our EAC. I have already established that in our previous videos. In which videos? The unbalanced Kelvin double bridge. If you have missed our previous videos, please do follow these videos. On that videos, I have separately considered or separately shown you all the parts of our equation that you will get from over here, and ultimately I have given you all those detailing part of our equation. That is why I have written this equation, because if I do repeat the same procedure, then that will be very lengthy. But I am more focused on the solution of this given given problems over here. So that is my motto. I need to solve this problem over here, and these are our given equations. So E0 is nothing but the difference of these two voltage elements over here. And how do we get to that? I have applied the Thevenin's theorem. So first I have got the open circuit voltage. So E0 is nothing but the open circuit voltage, and in our second part we have got our Thevenin's equivalent resistance that is been considered as our R0. And after I have applied after I have concentrated on our Thevenin's equivalent circuit, we have got the galvanometer current, or we can say that as a load current. So this galvanometer current expression is nothing but E0 divided by R0 plus G. If you have missed our previous videos regarding our Kelvin double bridge, please do follow our previous videos. On that videos, I have separately established all those equations over here. I am not skipping over here. Okay. Now in this present solution, we have concentrated that the small r value is negligible. So EAMD expression will be something else. So first the EAMD expression will be this one, which is R, and this small r part will be over here. So first I should write the expression that will be much more helpful for you. PR divided by small p plus small q plus small r divided by our r plus s plus our p plus q multiplied by r divided by P plus Q plus R multiplied with our EAC. Okay. As I have concentrated that small r value is negligible. Now if you do multiply over here as 0 multiplied with this factor, so this will become automatically 0. So at the numerator portion for our ratio, only r will be present over here. Similarly, for our lower portion, if you do concentrated that small r is 0, so 0 multiplied with this small p plus small q, that will ultimately give us the expression as 0. So ultimately, this is our expression for our present problem over here, as I have considered that small r is 0. So ultimately the expression will be this one. This one will be r divided by r plus s, and this one will be eliminated because of a small r factor over here. Okay. So ultimately I have got EAMD is nothing but our R divided by R plus S EAC. Okay. I want to repeat over here once again. This is our total EAMD expression over here. But in this present problem, as I have taken that the small r is negligible, so after I have put the expression for our small r as 0, I have eliminated this portion for our numerator and this portion for our denominator. As I have eliminated this both part of our expression, ultimately I have got the expression as r divided by r plus s multiplied with our EAC. So this is the expression for our EAMD. Okay, now if you do put the expression for our E0, so what is the ultimate expression for our E0? E0 is nothing but EAB minus of EAMD. So what is the EAB? EAB means our P divided by P plus Q multiplied with our EAC minus EAMD means R divided by R plus Q multiplied with our EAC. Okay. Now if you do take the common of our EAC, what is the expression we have got? EAC inside our bracket I do have P divided by P plus Q minus R divided by R plus Q. This one. Okay. So I have got the expression for our E0. So without knowing this expression, I think I should eliminate, or I will only consider the E0 over here. So I will eliminate the EAB and EAMD over here as I have utilized, or how to utilize that expression, that will be much more essential for us. I have already shown you over here, so I will only concentrate of our E0 over here. So I will eliminate this EAB and EAMD over here. Only the E0 expression will be sufficient for us, because we are more focused on our E0 expression or open circuit voltage for our Kelvin double bridge, and for our next part we do have the requirement for our equivalent resistance for our Kelvin double bridge, and ultimately we have got the galvanometer current, which is the main thing for us. So we need to eliminate our E0 and all this rest of the expression that will actually complicate your life. And why do we initiate these from this expression? Because conceptually, if your understanding are not clear, you are not been able to understand any part of our solution. That is why I have shown you how to change all this part of our expression, because these type of tiny things actually do have the bigger impact for your solution for any type of engineering application. Okay. So at this place, I will write the expression for E0 which I have got for this type of problem, which is nothing but E0 is our EAC multiplied with our P divided by P plus Q minus R divided by R plus S. This one should be S. I have written here the R plus S and I have written here the Q. Okay, just sorry for that. R plus S. This one should be R plus S. Okay. This one. I want to give you some amount of time to think about it, and after that I will do continue with our solution over here. I want to remind you over here once again. First I have taken that small r as 0, and after I have applied or put that value of small r as 0 in the EMD expression over here, the expression is further simplified, because after we do put the small r as 0, the modified expression for our EMD is this one, and I have put that expression in our open circuit voltage expression for our Thevenin's theorem, which is E0, and after that we have got this modified expression over here. So we no longer do require to remember the rest of the equations over there. Because of that I have removed or erased that portion over there, and I have finally got the voltage expression as E0, which is this one. And in our next part I will try to make our impression or try to show you the right path to how to get to that E0 expression over here. Hope you have understood all part of our solution, but if you still have any doubts, please let us know in the comment section. That will be much more better for you to understand in a more in-depth way, because if you don't understand this type of logics in a lot more in-depth way, then you are not been able to understand these subjects altogether. So just make sure do follow our classes, do subscribe our channel, and keep following our videos. So I will do continue this solution for the next part. In our previous part, we have shown you what is the exact step. I am just following you over here. So I have modified this equation of E0 over here, and rest of the expression will be same over here. And this one is our Thevenin's equivalent resistance. After we have applied that concept, we have got this is our expression. If you do follow our previous videos, you will get my points, and ultimately I have got the load current, which is nothing but the galvanometer current. For this present condition, I have got the expression as this one. Okay, now I am ultimately telling you over here that I am just erasing this portion. So what is the first thing, or what need to be followed first for this expression over here? That will be much more interesting part over here. What is the first step? You need to come out with your first step. First, we need to come out with our expression for our EAC. You can see EAC. Why? Because if you don't have that expression for our EAC, if you don't have that, you will not be able to calculate this E0 over here, as we have already got the P divided by P plus Q and R divided by R plus S. But before I go into that, now get back towards our problem statement. Determine the deflection of the galvanometer. We have got the expression for our galvanometer deflection when the unknown resistance R is changed by 0.1%. Now we need to alter the unknown resistance value or change of unknown resistance value over here, which is, as I have completed or changed the value of 0.1%, so ultimately the value is 1.001 multiplied with our, what is the value of our R in our previous consideration? The value of our R is 0.001. So this is our changing format for our R value over here. Now I am just utilizing our this calculator to have the value for our R, which is 1.001 multiplied with our 0.00001, and the value is 1.001. I'm writing over here The value is 1.001 multiplied with our 10 power minus 3. Okay, so this is our changed value for our R value over here, as we have changed the value just by 0.1%, and because of that consideration, the changed value for our R is this one. Okay, and the unit for this is this in ohm. Okay, now get towards our consideration for our EAC, because this is our times consideration for this part of our video. And how do you get to that? To get to that, we need to draw the Kelvin double bridge once again, because that do require the circuit diagram over here. So this is our P, and this one is our Q. Okay, and over here we do have, this one is our R, and this one is our small p, and this one is our small q, this one is our small r, and in between these two we do have, this is our standard resistor. Okay, now in between these 2 points we do have the galvanometer. So this is our galvanometer, and ultimately I do have, this is our bias resistor RV, and I can change that value of our bias resistor over here, and ultimately the battery will be connected for our given circuit. So this is our E. In this present problem, as the value of bigger P, bigger Q, small p, small q do have the same value of 1000 ohm, so all the current will be flowing in this path, in this given path. I have already told you about that. So the current is following only this path. So this one is our small r. Okay, now here this is our A point, this is our C point. We need to find out the voltage drop across this AC point over here. We need to apply the voltage division rule over here. And what is the voltage division rule? I have already told you in our previous classes for our circuit theory videos. If you have missed our previous videos, do follow our videos regarding our voltage division rule. Now I am directly telling you that what is the voltage division rule over here. The voltage at in between our AC point divided by our total, not that voltage, the overall resistance in between our AC point divided by our total resistance path multiplied with this voltage or total voltage E, that ultimately give us the voltage division or the expression for our EAC over here. So what is the EAC for this consideration? In between our A and C point we do have three resistor, R, smaller and bigger S. So what is the resistor? We need to write down over here, R plus S plus small r. Okay, divided by our total resistance. So what is the total resistance? In this case, the total resistance is quite frankly our RB plus R, RB plus R plus S plus small r multiplied with our total voltage, that is nothing but the E. So this is our expression for our EAC. Okay, now in this case you can see that as the value for our small r, R and S, small r value is negligible, so we can make that as 0, we can make that as 0. And once again, if you do consider that R and S value are very small, you can see that the R value is this 1.001 multiplied with 10 power minus 3, that is very small. And once again the S value is once again very small, which is 0.001. Okay, I want to repeat over here once again because this portion is very vital. In the lower portion for our ratio of this EAC expression, you can see that the R value is, after I have changed the value just by 0.1%, I have got that the R value is this one. So this value is very small, very small. And once again, this expression is present in the denominator. So this one is negligible. Why? Because this value is very small. So it has got the no power or no significance in this overall expression over here. So I can directly eliminate over here. For the same thing over here, once again, we do have that the standard resistor value has got the same value or very lower value over here. So we can directly directly say that this value is very small. So we can also say that we can eliminate, or that should be removed from our given expression. And the same thing is for our small r as well. Now what is the ultimate take we have got? The ultimate take is, so these three expressions will be eliminated, only RB will be present over here. And as in this given problem, we have taken that the small r value is negligible. So in the numerator part also, the expression will be given. So after I have considered this total expression, this is our final expression over here. Now I can put those values over here. So I am taking a very longer time over here. Why? Because if your concepts are not clear, you are not being able to understand the each and every detailing part of our expression or for our solution. That is why I am just going to show you all the parts over here. So I am just putting the R value over here, which is 1.001 multiplied by 10 power minus 3 plus S means our 0.001 divided by what is the value for our RB. The RB value is what? The 5 ohm resistor is included in the battery circuit, so RB is quite naturally the 5. That will be multiplied with our given voltage E, or the battery. So what is the battery? We have got 100 volt. So once again we are going to utilize the scientific calculator to have the value for our EAC, and that will be perfectly reflected on this given expression over here. So what is the value? 1.001 multiplied with 10 power minus 3 plus 0.001 divided by 5 multiplied with our 100. The value will be 0.040. Okay. The value will be 0.040. So this is our value. So we need to note down over here, because that value will be utilized for our future part for our solution. So the R value will be 1.001 multiplied with our 10 power minus 3 ohm. In our next part, we do have the EAC, which is nothing but the value will be our 0.040. Okay, I once again want to give you some amount of time to think about it, and once again like to suggest or reflect over here for the last time. After looking at this expression, you can see that we need to find out the EAC. Okay, and how do you get to that consideration? To reflect to that point, I have once again redrawn our given Kelvin double bridge circuit over here, and after that you can see that all the current is flowing in the at the lower part of our consideration. There should not be no current across our or towards or in between our P small p q small q portion over here. Why? Because all those values have got the same resistance values over here, so all the currents are going in this way, and we need to find out the voltage drop across our EAC. I have just applied the voltage division rule over here, and after I have applied that, I have got or I have modified those further expressions over there, and ultimately I have got the expression as R plus S divided by RB multiplied with E, and I have just put those values over here, and after that we have got the value as 0.040 volt. So this is our value over here, and I have already come out with our first part for 0.1% change for our R value over here, and ultimately this is our value. Okay. In our next part, I will do continue with our solution for our E0, then R0, and ultimately I will have the value for our galvanometer current. And at the last part, we will have the sensitivity expression, or what is the value for our deflection. That will be my ultimate destination point.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.